In the previous video, we talked about MIME types and the way in which an application could specify the manner in which it encoded each information. However, in many of the RFCs, the RFC specifies exactly how data should be encoded. In this video, we will look at some of those RFCs and look at the manner in which they specify how data should be encoded when transferred between two communicating hosts. As the first example of how an RFC specifies the representation of information, let's look at RFC 1939. That is the standard for the Post Office 3 protocol. If we just scroll down a tiny bit, we get to a description that you can see highlighted in yellow there. Let's briefly read it. Commands in the POP3 consist of a case-insensitive keyword, possibly followed by one or more arguments. All commands are terminated by a carriage return line feed pair. Keywords and arguments consist of printable ASCII characters. Keywords and arguments are each separated by a single space characters. Keywords are 3 or 4 characters long. Each argument may be up to 40 characters long. As you can immediately see, that's a very, very informal specification. It uses plain English to tell you what these commands look like, what they entail. The next portion that is also highlighted talks about responses, and it talks about the response code, the error code that is to be returned as a 3-digit value. The following paragraph talks about the possibility of having multi-line responses. So really, really informal, plain English specification of what the commands and the contents that are to be transmitted look like. Scrolling down a little bit further in that same RFC, we get to a slightly more formal but still extremely informal specification of what the quit command looks like, for example. You can see this is what it looks like. It consists of the word quit, no arguments, no restrictions, possible responses, and it gives you an example of what you can expect after you've used it. Going down just a little bit further gives us yet another example. That's the one that you use to retrieve messages. So retrieve message, that's the example, that's what it looks like. Earlier it said that message is a decimal number. So you would say something like retrieve 11. If you want to retrieve message 11, there's got to be a single space between the retrieve command and the number. It tells you something more about the arguments, something more about the restrictions, gives you examples and so on. So extremely informal. Ideally, one doesn't want to work with protocols that are specified as informally as this. So if we then move on to a following example, one that gives us somewhat more descriptive, more formal approach. Let's look at RFC 5321. That is the one that describes the simple mail transfer protocol. Now this is a much longer standard, and first example that we want to look at happens to be on page 15. So let's quickly go to page 15, and actually it's page 16. On page 16, you can see that it says SMTP commands and replies have a rigid syntax. All commands begin with a command verb. all replies begin with a 3-digit numeric code. Just scrolling down a little bit more, it says that there are some servers out there that explicitly want you to use uppercase. That's wrong, but maybe if you want to talk to those SMTP servers, you have to talk uppercase. So it's an option since you're allowed to use upper or lowercase. If you want to be fully compatible, you may want to use uppercase. Next useful information for our purposes appears on page 32. On page 32, you can see heading 4.1.1, and it talks about command semantics and syntax. And the highlighted part tells you that SMTP commands are character strings terminated by a carriage return line feed. The commands themselves are alphabetic characters terminated by a space, parameters follow, and a carriage return line feed otherwise. So this is beginning to look pretty much like what we've seen in the case of POP3, a rather informal description using plain English. But if we scroll down just a little bit, you can see that there is a formal specification. In fact, that is a type of grammar. And the grammar that is used is one that is based on the Bacchus-Naur form that was used to specify Fortran, and this is one that allows a bit more flexibility, so it's the augmented Bacchus-Naur form. In this example, there's not much to specify because it's basically the extended hello and the hello, and there are the examples that says you have to use the word EHLO, that's in quotes, followed by a space, followed by a domain or a literal address if you want to use the extended version, or if you just want to use the hello, it's the word hello in quotes, followed by a space, followed by the domain from which you are coming, followed by a carriage return and line feed. Going to page 36 to get an example. On page 36, you see a description of the data portion. In other words, the actual email that may be sent via the data command of SMTP. You can see that, again, looking at the highlighted portion, the mail data may contain any of the 128 ASCII character codes, although experience has indicated that use of control characters other than space, horizontal tab, carriage return, and line feed may cause problems and should be avoided. So here we see the limitation. You can send ASCII, but not all of the ASCII characters. Ideally, you should avoid most of the control characters. It also tells you that the message, as you probably already know, is terminated by a full stop on a line of its own. In other words, where there's a carriage return line feed that ends a previous line, then a full stop, and then a carriage return that follows this lone full stop. There is the syntax for the data command. It starts with the word data, and that's followed by a carriage return line feed, and that is then followed by the message until you get to the full stop. That was not specified in a very precise manner. There is one additional aspect of this protocol we want to look at, and that is on page 41, section 412, command argument syntax. So what this tells you is wherever it used some sort of an argument next to a word, whether that's a path or a domain name, here you can see a precise specification in augmented Bacchus-Naur format that describes all of those extensions, all of those parameters that can be provided. We're not going to go through it item for item, but you can see that it is indeed specified as a set of productions. The final example that we want to look at is RFC 2459. It is the standard that specifies the public key infrastructure for X509 certificates. Again, a fairly long specification, and first page of interest, page 5, it tells us that the profiles, the signatures in essence, are presented in the 1988 Abstract Syntax Notation 1 or ASN 1 specification. So it uses the ASN 1 specification to describe the format of messages that are signed using this key. More specifically, on page 15, you can see a specification of various entities that may be communicated. You can see that it looks pretty much like a grammar, and what you can see there is that a certificate is defined as a sequence, and that sequence consists of 3 values that are sent in as values following one another: a TBS certificate, a signature allocation algorithm, and a signature value. And to the right of that, you can see the data type of all of those. So we're going to look at ASN 1 in a bit more detail as we go along, just to show you that we've seen a sequence just now that is a constructor type. First highlighted one on this page is choice. So you can also use choice to construct types, and then the set and set of can also be used to construct compound types. And then there are the types that are atomic types that are not constructed. We'll look at how those are used just now. X509 that we've just seen in the RFC used ASN1 to specify the nature of data that is to be represented or to be transmitted. In particular, we saw that a certificate was specified using as a sequence, and the sequence constructor was used. And the sequence constructor basically said that the particular field or particular certificate would consist of 3 components. Just as a reminder, there are other constructor types as well. The constructor types would be choice, where you can say you have a choice here. You can either specify A or B or C, whatever choice A, B, and C are. Or it could be a set of A, B, and C. The word of makes a tiny difference. If you say it's a set A, B, C, then it means you have to use at least one of them. If you say set of, then you can use 0 to one of them. Any type that is constructed using a constructor operator is known as a construct. The alternative is a primitive type. And to talk about a primitive type, we would have our value that we want to represent, and it would seem as if that's sufficient, but actually the primitive type has a number of tags associated with it, so that the recipient knows what to do with what it receives. And the very first tag tells you what type of data you are receiving. It may, for example, be an integer or a real number or a bit string or whatever. All of those types of numbers, and the number more or less goes into the first field to indicate that this is the type of entity you are dealing with. The second tag or second field, it's an octet long, is the length. field. So it tells you how long is this content, how many octets does it occupy, and the content itself is what goes into that next field. And the length will depend on the type of object. If it's a character string, you may want 10 characters or 15 characters or 20 characters. Clearly, that's going to present you with a tiny problem if you, for example, want to represent 1,000 characters and you only have one octet for the length field to indicate the content. So we will deal with that challenge just now. One way out of that would be to put a special value in the length field where you say this is open-ended, I will mark the end of the content, and then you use a special end of content marker at the end. So if initially you say this is going to be 3 octets long, you will not mark the end of the content. But if you leave it open-ended, then you have to mark the end of the content. The length field, as we already indicated, may be problematic because if you only have one octet available, your maximum length will be 256, so far you can go. But we already said we have to put in some special values because you may want to say that it's open-ended, that you're not going to specify the length. So the fact is that it is actually split into a 1-bit and 7-bit field, and the 7-bit field tells you how long the content is. And the content can therefore only be up to 128 octets. However, one option that you have available is to mark it as a long content, and then what you can do is, rather than just using a single octet, you can, for example, say, I want 3 octets to specify the length. And that means the next 3 octets together, that's 24 bits, will be used to specify the length. So in that way, you have the option to have much longer types of data. If you want 1,000 characters, whatever, you just need to specify the length using these extended fields. Now, the coding rules that we are using now are some of the original rules, the basic encoding rules. Whenever you use ASN1, you have to say how the data will be encoded, what tags will be allowed and what will not be allowed. And the basic encoding rules is a very open-ended specification. It's a specification where you can say that I only want 5, but I want 25 characters of content, but I want 24 bits, 3 bytes to specify it in. Now, clearly that's a waste, but it is perfectly legal to do it like that. There are 2 other types, derivatives of the basic encoding rules, the canonical encoding rules, and also the distinguished encoding rules. And those limit what you can do. For example, they will limit you that you have they have to use the shortest possible way to represent a length. If you want to say 5 octets, you cannot space it out over 24 bits. You have to put it in that single bit length. Difference between the canonical and the distinguished rules is that one of the differences is that you can leave the content field open-ended in one of them, while you cannot leave it open-ended in the other one. You have to specify up front how long it's going to be. Also, if you have a set normally consists of a number of elements that can be in any sequence. But these rules, again, in one case, determine the order in which you have to provide the elements of the set. So it means if you use these 2 derivatives and you encode something, they will leave you with much fewer options, and specifically with the distinguished encoding rules, you will end up with one possible way to represent the data. Two other standards that you can go and look at to see how ASN1 is prescribed to be used. One is the LDAP standard that says you can use ASN1 with basic encoding rules. And the other example to look at is the SNMP standard, the Simple Network Management Protocol, that also says the values are encoded using ASN1, and again the basic encoding rules are used. So read a little bit through some of the standards where you find ASN1 to see how it is used. We don't see it all that often on the internet. On the internet we would more probably see MIME types, but it is definitely present. One of the aspects of a presentation layer that we've not said too much about yet is the ability of a presentation layer to translate content from one meaning to a different meaning. And one of the old favorites to talk about is a date like 1/4/2020. And the question is, what does that date mean? How does one interpret it? And in most of the world, that would be the 1st of April 2020. But in the United States, where they tend to switch the month and the year, that would be the 4th of January. XML is a format that we can also force fit into layer 6. And the reason I'm mentioning XML here is because it can easily represent that with an associated meaning. It's something that we've not really seen in any of our other examples. So if we have a date in XML, then we can easily encode it that we have a day, and the day would be, let's say, the 1, end of day, and yes, there are easier ways to write this, but that doesn't matter. It means I've just taken that date, interpreted it in my context, and encoded the 1 as the day. And similarly, I can encode the month as a 4, and that's the end of the month. And the same with the year, and that would bring us to the end of the date. The point of this example is that I can mark my data up with semantic meaning, with semantics, and if I've done that, it can be interpreted at the receiving end. As I said a moment ago, this enables one to transmit content, mark it up in the way in which you intend it to have the meaning it should have, and then at the receiving end, it can be unpacked and represented in the way in which it makes sense at that end. One should always remember that the presentation layer is part of the ISO OSI specification, and it was never really part of the TCP IP specification. So in all of our examples, we are sort of force-fitting things into the presentation layers that were never intended to function as a separate presentation layer. So to some extent, all the examples are artificial, but they do give you a feeling for what one would expect in a presentation layer. This brings us to the end of our discussion of the presentation layer. Obviously, there is a lot that we haven't covered, and you'll have to read much wider to understand everything, to really get to grips with what can go into the presentation layer. Look at the various RFCs, look at the way in which they talk about representation of data, and that will give you a much better feeling for how data is represented, in particular on the internet, but also in the wider networking context.
Music